Good morning, everyone. I hope you can hear me.
Good morning, sir. We can hear you.
Right. So today we are going to resume from where we left off in our classes on the topic of the microarchitecture inside the processor. So we are looking at the MIPS ISA, and we took a subset of the instructions, which are R-type instructions, load word and store word instructions, and the branch if equal instruction to have a look at the microarchitecture. Because if we take all the instructions at the same time, it's difficult to understand and get the grasp of what's happening. So we are only taking a subset of instructions which are covering most aspects of the microarchitecture. So based on that, this is the place where we ended up last time. So this is the data path with control unit added for the mentioned instructions: R type, load word, store word, and branch if equal instructions. And then we had at the end of the last class we had a discussion about what these control signals are. What these control signals are, what are their purposes. So that is what we ended up doing in the previous class. Let's bring up the pointer. Okay, right. So these are the control signals that we were looking at, and this is the data path for the given instructions, for the instructions that we were discussing: R type, load word, store word, and branch if equal instructions. So we had the instruction fetch elements here from the instruction memory using the program counter, and then you decode the instruction. The control unit derives all the necessary control signals, and you access the register file in order to read any register operands that are required, or you take the immediate value given in the instruction and do sign extension on it, and then go to the ALU to perform any arithmetic or logical operations that are required. And if it's a memory related instruction, you go to the memory to do a read or a write. And if there is a result from the ALU or the memory, you take it and write it back to the registers. And also at the very end, you, based on this, whether the instruction is a branch or a jump instruction, you manipulate the program counter using any immediate offset values given in the instructions. That was the general idea. And the control signals given here, 8 control signals, total 9 bits, because ALU op is a 2-bit signal. So all these control signals are regulating this data path to make sure that all instructions are working properly. So that was where we left off last time. And right, so today we're going to talk about how to generate these control signals. So the control unit needs 12 bits of inputs in total. So the major part of that is the opcode given by the instruction. That is the most significant 6 bits of the instruction, which is the opcode. So almost all the control signals can be generated with just this opcode, but for R-type instructions, you also need the func field that is the least significant 6 bits of an R-type instruction, which defines what ALU operation or what mathematical or logical operation that you need for that particular instruction. So these 12 bits together serve as inputs to our control unit. Then using those inputs, the combinational circuitry inside the control unit generates 9 bits of output altogether, 8 control signals. One of those is a 2-bit signal, so 9 bits altogether. 9 bits of output corresponding to the blue signals that we saw in the previous diagram. Then, like I told you in the previous class, this is what we're looking at. This is a combinational circuit which has 12 bits of inputs altogether and 9 bits of output. So you can draw a characteristic table and use the standard methods that you have learned in CU221 digital design to make or derive Boolean functions for these 9 bits of output and come up with circuitry to do this, which you will have to do for your own processor design in lab 5. It's a different design, a simpler design. But for that also you need control signals, and you use the same methods. You decide what inputs you need for the control units, what output you're generating, and then come up with a combinational circuit to do that. So you already know how to implement that. Right. So yeah, so this diagram shows what we were discussing so far in this slide. So you only need the most significant 6 bits, which is the opcode, and the least significant 6 bits, which is the func field or the function field for R-type instructions. So with those inputs, you can generate this set of control signals. Right. So this control unit, the circuitry, is responsible for setting the correct values for those control signals that we just discussed, those 9 bits of output, setting the correct values on those outputs to make sure that your instructions are executed properly. Then, right. So to understand what control signals are relevant for what instructions and how each instruction is handled within our microarchitecture, what we are going to do is we are going to take our subset of instructions, R-type, load word, store word, branch if equal, those subset of instructions, and we are going to look at how each of these instruction is handled inside the microarchitecture, inside the data path, and how the control unit generates the signals for each of these instructions. So that is what we are going to do now. Right. So yeah, so this is the R-type instruction, the data path elements used by the R-type instruction. You can see that some elements are faded out on a lighter gray color, which are not used by R-type instructions. So some black data path elements like the memory is not used by the R-type instruction. The sign extension device, sign extension circuitry, which is actually a very simple circuitry, like we discussed that in the previous class. So that is also not used by R-type instruction because R-type instructions don't have immediate values. Then this particular circuitry, the adder and the shifter in the instruction fetching mechanism, is also not used by R-type instructions because R-type instructions will not modify the program counter. This circuitry is used by the branch instructions, which is going to modify the program counter. So these faded out elements are not used by our R-type instructions. So what happens is when an R-type instruction is fetched from the instruction memory based on the program counter value into the control unit will look at the most significant 6 bits, that is the opcode, to generate this series of signals. Then it'll also need to look at the least significant 6 bits, that is this instruction words bits 0 to 5, which is the function field. Function field is needed to generate the signal to select what operation you need from the ALU. So the control unit will look at the instruction and generate all these control signals. Then in an R-type instruction, you have 3 register operands, 2 to read and 1 to write into. So the reading operands, you are reading from the register file by providing the register numbers or register addresses into the register file and getting the appropriate values in those registers from the 2 data outputs of the register file. And the ALU will perform the necessary operation based on the control signal on the two register operands coming from the register file, and the result needs to be written into the register file at the end. You're not going to modify the program counter. The program counter is automatically incremented by 4 with the instruction fetching mechanism. So why are you incrementing it by 4? Each instruction word contains 4 bytes. So this is the byte address presented inside the program counter needs to be incremented by 4 to get to the next word. Right. So here what you're seeing is the format of the R type instruction. The first or the more significant 6 bits are opcode. Least significant 6 bits are the function field, which are used by the control unit. These most significant 6 bits and the least significant 6 bits. And you have 3 register operands: the destination register in bits 11 to 15 and 2 source registers or reading registers addresses presented in bits 16 to 20 and 21 to 25. So we have 3 register numbers or register addresses, 2 reading and 1 writing. Then if this is a shift instruction, the shift amount is provided in bits 6 to 10. Right. So let's take a simple example and see how the control, what are the control signals, how the control signals behave for this instruction. So let's take this add instruction, add 1, 2, 3, $1, $2, $3. So the idea is add the values in registers number 2 and number 3, save the result in register number 1. So register number 1 is the destination register corresponding to this RD field, and registers number 2 and 3 are the 2 operands, 2 reading registers corresponding to RS and RT. So if we encode this add instruction, this particular add instruction, the instruction word will look something like this. So add is the opcode should be corresponding to add, which is an R type instruction, and we know that the opcode for all R type instructions are 0. And the funct field for add instruction is 32. So these things we had a look at in at the end of the last class when we discussed about the ALU control. So funct field for add is that 32, and the ALU control signal should be generated by the control unit based on that. Right. So we have opcode 0 and funct field 32. This indicates that we are doing an add operation, and shift amount is set to 0 because we are not doing a shifting or a shift instruction. So the remaining fields here are the register addresses. So RD, destination register, is register number 1. So the value, the address is 1, register 1. That is the number, register number or the address in the register file. Then this is the first source, first reading register, RS. So RS, the register number is number 2 in binary. And that means this is the address within the register file of the register number inside the register file. Then RT field is the second source register, number 3, and that is register number 3 there represented in binary. So now I want you all to do a little exercise with me. Let's try and fill this table. We have register, the register destination branch, memory. So these what we have here are the control signals generated by the control unit using the opcode. And then looking at our data path here for the R type instructions, let's try and figure out the values for these control signals. So right, So let's take the first one, register destination. What does this control signal do? It goes into this mux at the in front of the register file. What it does is decide which register, where is the register to be written provided in the instruction word. So you can see that there are two inputs into that instruction, into that multiplexer. One is bits 11 to 15, input 1, and input 0 is bits 16 to 20. So here, the destination register, the register that you're writing to is register RD, even in this field, bits 11 to 15. If you recall in I-type instructions, if you have a destination register, that destination register is given in bits 16 to 20 in I-type instructions. In R-type instruction, the destination register is given in bits 11 to 15. So this control signal register destination decides where the destination register is given in the instruction word, whether it's in bits 50, bit 11 to 15 or bits 16 to 20. In our case, for R-type instructions, the destination register is given in that field, bits 11 to 15 of the instruction word. So in order to select this input from the multiplexer, we need to send what value here? What is the value we need to send on this control signal, register destination control signal, in order to select this input? Can someone tell me? 0 or 1?
1.
1, yes, that is correct. So if you send a 1 on this blue signal here, you will select that input 1, and send it to the right register address in the register file. So the value of register destination signal should be 1. So let's fill that in. It should be 1. And right, so what about the branch control signal? What does it do? Branch control signal, it goes from here into this AND gate, which is taking the 0 output, whether the result is 0 from the ALU, and perform AND operation and send it to this multiplexer. If the result of this AND gate is 1, the multiplexer will take this grayed out 1 input, which is basically for branch instruction. So the branch control signal, what it does is decide tell whether the instruction we are dealing with is a branch instruction or not. In other words, whether we need to take the result of this adder in from the multiplexer to update the program counter. Since this is an R-type instruction we are dealing with, we don't use the branch circuitry to deal with branch. So we need to send a 0 from this branch control signal into this AND gate. So regardless of the value coming from this 0 output, you will get a 0 output from the AND gate, and that will take this normal input or 0 input into the multiplexer and send it to the program counter. That is only incremented by 4. Program counter will only be incremented by 4, which is what we want. So the value we need to send in the branch field or the branch control signal here is 0. That should be 0. Right. Okay, finally. So next, mem read control signal. What does it do? Mem read control signal is sent to the data memory device to read from that. We only need that for a load word instruction when we read from the memory. So here that is a read control signal. We don't read from the memory, so that value also should be 0. Right. Then mem to reg control signal. What does that do? That controls this multiplexer. If the value of this the mem to reg signal is 1, we will take the output of the data memory and send it to the register file. That is, if we are reading from the memory. Since our R-type instruction does not read from the memory, we need to send a 0 value on this mem to reg signal to take the output of the ALU and send it to the register file to be written. So what this multiplexer does is pick between the output of the memory or the output of the ALU to write to the register file. So for R-type instruction, we need the output of the ALU, which is the 0 input. So we need to send a 0 along this mem to reg signal. So the value of this is also going to be 0. Right. So next, ALU up. ALU up is the 2-bit signal sent to this ALU control to decide what type of instruction we are dealing with. And if you go and have a look at our previous slide where we talked about the ALU control, the value for ALU up for R-type instruction should be 1 and 0. So this is only considering our subset of instructions. So value for ALU op signal, the 2-bit signal, is 1 and 0. And when the ALU control circuitry receives that, it will also look at the func field, since this is an R-type instruction, and generate the ALU control signal accordingly. So right. So R-type instructions, the value to be sent by ALU, sent along this ALU up control line to the ALU control should be 1, 0. So to denote R-type instruction. So what we have here is the value 1, 0. Right. So next we have memory write. Mem write control signal. That is this. Mem write goes to the data memory. That is when we are writing to the memory. This is a write control signal. Only when this control signal is high or set to 1, we can write to the data memory. So since we in R-type instructions, we are not writing to the data memory, the signal should be set to 0. So the control unit needs to produce a 0 output on that mem write control signal. Then ALU source, ALU SRC. What does that do? ALU source, this is a select signal for a multiplexer. So what does that multiplexer do? Decide between the second output of the register file or assign extended immediate value coming from the instruction itself to send to the second operand input of the ALU. So if we produce a 0 along that control line, we'll take the 0 input of the multiplexer, which is the register file output. If we produce a 1 here, we will take the immediate value output, immediate value input into the multiplexer and send to the ALU. For the R-type instruction, we need to send this register file output into the ALU. So we need to send a 0 to this multiplexer. So ALU source signal should be a 0. Right. And reg write signal. Reg write signal is the write control signal into the register file. That is when we want to write something into the register file. Are we writing anything in R-type instructions? Yes, we have a destination register address provided through this multiplexer, that is the write register address. The value to be written is provided by the ALU from along this line here, and the control signal should be set to 1 in order to write this value to that register address. So we need to send a 1 in order to write to that register. So the value here is 1 because we are writing to a register in a register file. Okay, I hope that example was clear and you can understand how the control signals regulate the data path for that R-type instruction. Do you have any questions at this point? Are there any questions at this point? No? Okay. Right. So next, what we are going to do is what we are going to do is, just like we decided the values for these control signals for R-type instructions, let's go and do that for branch if equal instruction, that is BEQ. Now, as an overview, we have the data path elements used by this branch if equal instruction. The instruction fetch mechanism, you go to the instruction memory, using the program counter value, fetch the next instruction, and that instruction is a branch if equal instruction. Then looking at the opcode, we need to come up with these control signals. Now, branch if equal instruction, what it does is subtract a given register value from another register value. If the result is equal or if the result is 0, then branch to the place given by the offset immediate value. So we have an immediate value in the instruction, which is coming along here, bit 0 to 15, and then 2 register operands going into the register file. Right. So in the next slide, we'll have the format here. So this is an I type instruction, immediate type instruction. So still the opcode is the most significant 6 bits. Then we have 2 register addresses, the 2 read registers. We are not writing to any register. The immediate field will give the offset, how many instructions you need to jump forward to compare to the current program counter value. That is the format of the branch if equal instruction. So we take the 2 register addresses, read from the register file, send those register values into the ALU, and if the 0 output of the ALU is set, or 1 set to high, meaning the result was 0, we use that as an input to the AND gate here, and using this branch control signal, we generate a 1 signal here, and thereby use the result of this adder circuitry. And what is the result of that adder circuitry? You take the regular update to the PC, that is PC plus 4 coming into that operand, that input of the adder. The other input is the immediate offset, sign extended and shifted to the left by 2. Sign extended because the immediate value is only a 16-bit value, we need a 32-bit value. So sign extended and shift it to the left by 2 in order to make it a word address. Sorry, in order to make it into a byte address, because the offset is talking about how many instruction words you need to jump to, but the value in the PC is a byte address. So you need to shift to the left by left by 2, because one word has 4 bytes, 2 to the power 2. So shift 2 positions to the left. Then add those two together, add the offset to the regular PC increment and get the result, put it into the program counter. We are not accessing the memory, that is grayed out. We are not using the result of the ALU other than the 0 output. So that is grayed out. And we are not using the write circuitry into the register file. We are not writing anything into the register file. Right. So now I want you to take 5 minutes and fill this table, the values for these control signals based on this instruction example. Branch if equal, register 1, register 2, offset is 100. That is, if the values in registers 1 and 2 are equal, jump 100 instructions forward by manipulating the program counter. So can you take 5 minutes, come up with the values for this register control signals and tell me. I'll give you 5 minutes. Look at the diagram. This should be available in the slides I uploaded into Moodle also. So have a look at that. Fill the table and tell me the values. Okay, Vishwa is asking, how can we calculate the immediate value? Can you clarify that question, please? You can unmute yourself and ask. So the immediate value is the least significant 16 bits of that instruction, right? So that value tells what how many instructions to jump forward or backward in the branch instruction. So if we go and have a look at the format here, right? So value 100, that is 100 in binary 16-bit number. So we have leading zeros here. So we'll take that. Let me clarify the question again. One input to the AND gate is always 0. Isn't output of AND gate? Okay, so I think there's a that's a different question. I'll answer that. Right. Okay. So for Vishwa's question, this value, if you write your code in assembly, you have to give the value here, right? If you write your code in machine assembly, you have to specify the value here, how many instructions to jump forward. So here we have 100 given in binary. Or else if you write in textual assembly, then you can also write this like that. Branch if equal, these registers values, if they are equal, branch 100 instructions forward. If you know exactly how many instructions you want to jump forward or branch forward based on this computation. But when you're writing assembly code, for convenience, you use labels like exit or loop end or loop beginning or anything, right? So you can use those labels here. So in that case, what happens is the preprocessor of the assembler should assign a value to that label. What is the value of exit? If we have branch if equal $1, $2 exit here, the value of that exit label should be calculated by the assembler. How many instructions you need to jump forward in order to reach where that label is put. So that is the task of the assembler, to get the instruction sequence for the program counter value that should be here, which number of instruction in the sequence of execution the current instruction is, the next instruction is. So the program counter will have the value for the next instruction. how many instructions you want to jump forward in order to reach the instruction given by the label exit or the label loop end or whatever the label is. So it's the job of the assembler to subtract those two and get the value and put it in the instruction. I hope that clarifies your concern, Vishwa. And then there's another question. One input in AND gate is always 0. Isn't the output of AND gate always 0 every time? No, because this is the signal's name is 0. Its value is not always 0. The purpose of this signal is to say whether the output or the result of the ALU was 0 in the current operation. If it was 0, the 0 signal will be 1. If the result is non-zero, the 0 signal will be 0. I hope that clarifies the second question. Right. Okay. So right now, let's have a look at our control signals value. I hope you went and decided the values needed on these control signal outputs generated by the control unit for branch if equal instruction. Okay. Can someone tell me the values needed by values generated by the control unit on these signals? Register destination, what should be the value? What do you think? It's okay to be wrong, doesn't matter, we are still learning. What do you think? Well, you had to have 0 or 1, one of the two. Is it 0 or is it 1?
It is doesn't matter, I think, because reg write is disabled in this situation.
Yes, exactly. It doesn't matter. We don't care because we are not writing into that register address. We are deasserting or clearing this signal. We are not writing to the register file. So doesn't matter whether the instruction words bits 16 to 20 or 11 to 15 are sent to the write register address. We are not writing to that register. So it doesn't matter. We don't care about it. So here, yeah, the value doesn't matter. We don't really care. Right? So can put an X. So what about the branch signal? Branch signal that is going into this AND gate. Yes?
It should be 1.
It should be 1 because we need the output from this 0 signal to be sent to the mux. If it is 0, the output should be 0. If it is 1, the output of the AND gate should be 1. Right? So we are sending 1 along this branch control signal. Right. 1 there. Memory read. What is the value? Memory read, mem read. Control signal. Mem read and mem write both. Let's take them at the same time. Write and read control signals going to the memory. Are we using the memory?
No, they should be 0.
They should be 0. We are not reading from the memory or we are not writing from memory. So this is 0. And mem write should also be 0. We are not dealing with memory in this branch if equal instruction. Then mem to reg. Mem to reg here. Mem to reg is a control signal going to this multiplexer. Whether we take the memory output or the register, the ALU output to be sent to the register file to be written to. What should be the value of this mem to reg control signal? It's very similar to our register destination control signal. Yeah. Can you tell me?
Yes, it is matter.
It doesn't matter. We don't care. So mem to reg is again a don't care. Having that as don't care will make our Boolean expressions simpler and circuits easier to build. So easy to simplify. So ALU op, what should be the value for a branch if equal instruction? ALU op value, that is this 2-bit control signal going into the ALU control to ask the ALU to perform a subtract operation on the 2 register operands. What should be the value? So if you scroll backward in our ALU control, you can see that for branch if equal instruction, the ALU op signal is set to 0, 1, and we are looking for subtract operation. For load word and store word, we set the ALU op to 0. We are asking for add operation, right? So we want this 0, 1 value in our ALU op control signal for that example. Yeah. So this is 0, 1. Right. So ALU source control signal. Somebody tell me the value. ALU source control signal here. This line. What is the value?
It should be 0.
Should be 0 because we are taking the 0 input register file read value into the ALU, that is the second operand, not the immediate value, right? Immediate value, we do have an immediate value in the branch instruction, but that is to manipulate the program counter. That is the address offset. It doesn't go into the ALU. ALU does a subtraction on the provided 2 registers, right? So ALU source should be a 0 to get the register operand instead of the immediate operand. And register write signal, this one, what is the value?
It is 0.
It's 0 because we are not writing to the register file. So that is 0 for the branch instruction. Right, brilliant, perfect. So I hope that clarifies how the data path elements are used by the branch instruction and pretty much any branch instruction by setting the control signals. Somebody is asking a question. Do we need to remember the tables like in slide 26, which is the ALU control value? No, you will not be expected to remember. Say you need ALU of 0, 1 for branch instruction. So that doesn't have any value remembering those things, but you might be expected to say you must be given the signal values and expected to derive the Boolean expression. So expected to come up with a combinational logic circuit to generate those control signals. But yeah, you are not expected to remember values for that particular example, right? That we are only taking an example, a very simple subset of the MIPS instruction to understand this. So you're not expected to remember those things, but the logic behind all these decisions you're supposed to know, understand. Okay, so right, so that is the branch if equal instruction. So we went through all the control signals. Do you have any other questions before we move on to the next type of instructions? Okay, I'll take that as a no. And right, so the next is load word instruction, which is loading a data word, 32-bit word from the data memory into the register file. So load word instructions, there are I type. The most significant 6 bits are of course the opcode and the opcode for load word is 35. Load word instruction, the opcode is 35. We had a look at that sometime earlier on. Load word is 35, store word was 43. So we had a look at those numbers because that is the subset of instructions we are looking at to understand the execution. Right, so we have the opcode 6 bits there, 2 register addresses, 2 register numbers, and an immediate value, 16-bit immediate value. So if you write the instruction, the format is something like that: load word, register number, immediate value with a register number. So what that does is go to this address given by this this expression here. $9 is the base register, base address. That is this RS here, right? Base address. Take the base address stored in register number 9, add an offset of 32 to that, 32 words, add an offset of 32 words to that, and go to the memory, read from that total address, and get the result, save it in register 8. Register 8 is a destination register given by this RT field, right? So bit 16 to 20 in this case is the destination register. We are going to write to that register. We are going to read from this register. That what we are reading is the memory address value, a 32-bit memory address value. Then we need to add this immediate offset into that base address value, go to that address in the memory, read, get the result, and write it into this destination register number. Right. So taking this example, load word $8, offset 32, base register value $9. So here this is the destination register number 8. This is the base register number 9, and that is the immediate offset 32 given here. So based on that particular example, can you guys take another 5 minutes to derive the values for these control signals? So what will happen is the instruction will be fetched, the load instruction will be fetched based on the program counter value. The control unit will look at the opcode, see that it is 35, that this is a load instruction. Based on that, it will define the values for these control signals. And you are reading one register value, which is the base address stored in that register. Take that into the ALU, take the immediate offset given in the ALU, send it to the multiplexer, sorry, send it to the ALU, add the immediate offset into the base register value, take the ALU result, which is the memory address that you want to access, go to the memory with it, read from the memory, take the output, write it in the registers. That's what the load instruction does. Can you tell me the values for these signals? Shall we have a look at the value? What is the value of the register destination control signal? Can someone tell me?
It's 0.
It's 0. It's 0 because the destination register's address is present in bits 16 to 20, not bits 11 to 15 in the instruction word. So yeah, we need to send a 0 in this through the select signal to get that into the right register. So this is 0 for our load word instruction. Then branch, what is the value?
It's also 0.
It's also 0 because this is not a branch instruction. We will not be writing anything into this adder circuitry. We will not taking that adder's output to manipulate the program counter. This is not a branch instruction, so the control signals value should be 0. Right. So okay, mem read control signal.
It is 1.
It is 1 because we are reading from the data memory this time, right? So we need to send a 1 here, read control. So mem read is 1, and on the same note, mem write, the value of mem write signal is what?
It is 0.
It's 0 because we are not writing to the memory, we are only reading. Right. Okay. So while we are on that, make a note that if we want, we can write and read to the memory at the same time. So which we will need in a later topic. But for now, no, we are only reading, we are not writing. So that's that. And mem to reg control signal into this multiplexer. What should be the value?
It should be 1.
It should be 1 because the number one input is what we are reading from the memory. Number 0 input is the result of the ALU. We only need the read value read from the memory to be sent to the register file. So control signal should be set to 1. So that is 1. ALU up. ALU up was set to what?
0, 0.
0, 0. For load word and store word instructions, what we are doing is adding an offset to the base address. So addition operation. So ALU up signal is set to 0, 0. So how do we know that? That is how we have defined it in the previous slide when we started looking at the control unit. Okay, so ALU source, that is this control signal. What is the value for the load word instruction?
It should be 1.
It should be 1. We are not reading a second operand from the register file to be sent to the ALU. We need the immediate offset value sent to the ALU. So the multiplexer should be selecting the 1 input here. So that should be 1. And register write control signal. The value is what?
It should be 1.
It should be 1 because we are writing to a register. We are reading something from the memory and writing that to register. So register file. So yes, register write control signal should be set to 1. Perfect. Brilliant. So to wrap up this particular exercise, so we had a look at R-type instructions, branch if equal, and load word. So I want you all to take 5-6 minutes, draw the relevant data path elements and the control signals which are used by a store word instruction. So that is, draw a diagram like this for store word instruction. You don't need to draw the not relevant part, non-relevant parts of the data path. Only draw the relevant parts of the data path and come up with the values of the control signals. So draw a diagram like this for store word instruction, excluding anything that you don't need. Once you have done that, you can fill the table for the control signal values which are needed for this particular instruction. Store word 8. This is there's actually a mistake here. This isn't $32. It should be just 32. So just scratch that out. There's no dollar there. Just 32 and $9. So base address is register number 9. Add an offset of 32 to that and go store the value in this register, store the value from this register into that memory location pointed to by that address. So that is what the store word instruction is. So you can go look at the instructions encoding here, or code source register where the original value is, and this is RT is the source register, the original value is. RS is the base register, or the where the base address is stored. Add an offset of 30 to that this is wrong. This should be 100. There's a mistake here. So let me correct that on the slide itself. Yeah, can we get the values for the destination register control signal?
It should be 0.
It should be 0. Can you also tell me why it should be 0? We'll have a look at the load words data path diagram. So register destination is here. This control signal.
Because the destination register is RT, the bits for that register is 16 to 20.
Yes, so but that is for the load word instruction. We are talking about a store word instruction. Do we have a destination register in a store word instruction? In a store word instruction, what we do is compute an address, memory address, based on this base register and the immediate offset. Take the value given in this register, the source register, take it and store in that memory location pointed to by the computed address. So in essence, we are not writing to the register file. We are reading something from the register file and writing that to the memory. Yes. So in that light, what should be this control signal's value? In fact, 0 is not wrong, but
It doesn't matter.
it doesn't matter. It doesn't matter whether it's 0 or 1 because we are not writing to the register file. Yeah, that is correct. So it doesn't matter whether we send a 0 or 1 here. So 0 is not wrong, but the best answer is we don't care. We are not writing to a register in the register file, so we don't really care about it. So this should be an X, and branch,
It should be 0.
it should be 0. This is not a branch instruction, right? It should be 0. Can someone tell me the values for these other instructions as well altogether? Memory read, what is it? What is the value for that control signal? Memory read this, that is memory write. This is mem to reg. What are those values? Who can tell me?
Memory is 0.
Memory is 0. We are not reading from the memory. We are storing to the memory or writing to the memory. And what about mem to reg? Mem to reg, that is this. To decide whether we are writing the data memory result or ALU result into the register file. Value here is
It should be 0.
it should be 0. Should it be 0? If we send a 0 here, the 0 input is the ALU result. What is the ALU result in a store word instruction? The ALU result is the base register value plus the immediate address offset, which means the result is the memory address which we are sending to the data memory. Yeah. So if we take that address here and send a 0 control value here, we are sending the address, memory address into the write data value part of the register file.
No, it should be 1.
It should be 1. If we put 1 here in the control signal, we are taking a read data value from the memory and sending it to the write data value in the register file. So since we already set the memory read control signal to 0, we are not reading anything from the data memory here. So what we will have in this input here is some garbage value, right? We don't know what that value is. And that garbage value will be sent to be written to the data, write data port in the register file. So what is the whole point of what we're trying to do there?
It doesn't matter if it is 1 or 0.
It doesn't matter whether it's 1 or 0 because we are not writing to the register file. We said it doesn't matter what we are sending here. Likewise, it doesn't matter what data we are sending from this multiplexer because we are only writing to the memory, not reading from the memory. So this input doesn't make sense for this particular instruction. That input, the ALU result, doesn't make sense for this particular instruction. So it doesn't matter. We are not going to be writing to the register file anyway. We are going to send a 0 on this register write signal. So for a store word instruction, this is don't care. We don't care. So for a store word instruction, mem to reg is don't care. And register write is also 0. We are not writing to the register file. So I hope that example made clear of the point that if we do not put a 0 in this line for the store word instruction, some garbage value may be written to some random register which we don't really know about. Yes. So the values of this field 16 to 20 or 11 to 50 are not supposed to be destination registers in this store word instruction. So some address will come here because we will be sending either a 0 or 1 along this control signal. We don't care. Some address will go into that port. Some value will go into this data port, data input, either from the data memory or the ALU based on that control signal, because that is also don't care. So if we do not set a 0 here, something will be written to some register and corrupt the value in that register. So make a clear note of that point. So we have to send a 0 here, otherwise the data in our register file may be corrupted. So ALU op for the store word instruction is the same as load word, should be 0, 0. We are asking the ALU to perform the add operation, and mem write should be what?
It should be 1.
Mem write should be 1 because we are writing to the memory. Mem write should be 1. We are writing to the memory in a store word instruction. And ALU source control signal for the store word.
It should be 1.
It should be 1 because the address offset is given as an immediate value. That should be sent to the ALU. Base register value plus address offset value. So ALU source should be 1. Mem write should also be 1 for a store word instruction. Okay, so that completes the set of control signals. And yeah, so you can draw the data path and control diagram for store word yourself. Right. Okay, now we have the data path and we understand how it operates for load word, store word, R type, and branch if equal instructions, which uses the hardware that we had a look at so far in our data path and control. So that covers basically 95% of the hardware required to implement the MIPS ISA in a single cycle processor implementation. So what we left out was jump instructions. So how do we implement jump instructions? So the encoding of jump instructions are like this. You have the 6-bit opcode for the jump or the J instruction. The opcode value is 2. JAL or jump and link instruction, the opcode value was 3, defined by the MIPS ISA. So the rest of the instruction, the 26 bits, are the address offset, a word address to be jumped to. So jump uses a word address offset as an immediate value. Size is 26 bits, given in the least significant 26 bits of the instruction itself. And how do we use this? We should use this to update the program counter with the concatenation of these elements. So the program counter should hold a 32-bit address in the instruction memory, right? Program counter holds a 32-bit address, which is some location in the instruction memory. So these 26 bits we need to manipulate and get it into 32-bit byte address. So this is a word address. What we have here in the immediate value, 26 bits word address. And in order to make it into a byte address, we need to add or append 2 more bits at the end of it. 2 zeros. We are not interested in whether we need the first byte of the word or the second byte or the third byte or the fourth byte of the word. We need the entire word. So we add or append 2 zeros at the end of these 26 bits to make it into a byte address. Now we have a 28-bit address. What about the most significant 4 bits? We are using the existing bits in the original program counter value, that is PC plus 4, current program counter plus 4 value. Take that and take the most significant 4 bits of that, because we are making the jump with respect to the current program counter value. Current program counter value will hold something which is the address of the next instruction, one after this jump instruction. We need to go and add an offset saying, okay, we need to jump 100 instructions forward or 100 instructions backward. So what we need to add there is take the most significant 4 of the existing PC plus 4 32-bit value. Right. Now, in order to get this concatenated value into the program counter, we need another extra control signal generated by our control unit, in addition to the 9 control outputs that we looked at so far. So this is the data path and control, including the jump instruction. Now, for the jump instruction, we don't need the register file. We are not reading from the register file. We are not using the ALU. We are not reading the data memory. And we are not using the regular 16-bit immediate value in I-type instructions also. Our immediate value for the jump instruction is a 26-bit value. So we need to take that separately. So what do? We take the 26-bit value, shift it to the left by 2 to make it into a byte address. So we get a 28-bit byte address. And we take the top 4 bits of the PC plus 4, that is the regular next instruction value, PC plus 4. Take the top 4 bits of it, bits 31 to 20, or bits 28 to 31, the most significant 4 bits, and concatenate it with the 28-bit byte address offset. So concatenate that, and then you have the jump address, the 32-bit jump address going into this multiplexer. Now we added an extra multiplexer here. The old branch instruction and the regular instruction fetch mechanism had PC plus 4 going into that multiplexer, or PC plus 4 with the added 16-bit offset for a branch instruction going into that multiplexer. So now we need to decide whether we need the regular PC plus 4 input here, or the regular branch offset added input coming there, or this new jump target address coming through there. To decide that, we need a multiplexer control signal, that is this jump control signal. So looking at the opcode, if the opcode is 2, or if this is a jump instruction, then you need to set this control signal high, or set it to 1. So you take the 1 input, which is this new concatenated address, and send it to the program counter. So that is how you add the elements for the jump instruction into the data path and generate the necessary extra control signal. So these other control signals are mostly don't care, because we are not using. And register write, no, 0. We are not writing the register file, not writing to the memory, not reading from the memory. And you have to pay careful attention to these write control signals, or otherwise you may be corrupting data in the register file or the data memory by writing garbage values into random addresses. So that is the data path with the jump instruction added, and that completes the data path. And for certain other variants of branches and I-type shifting instructions and all that, R-type shifting instructions and all that, you may need a few extra control signals, a few extra paths in this diagram. You can add them by looking at the instruction and its encoding. But this covers nearly everything that is done by a MIPS, single cycle MIPS CPU. Right. So the data path that we looked at, it contained all the functional units and connections or buses necessary to implement our MIPS ISA as a single cycle implementation, meaning everything is done within a single cycle. For our single cycle implementation, we had two separate memories, instruction memory and data memory, one ALU, some extra adders in the instruction fetch mechanism, and lots of multiplexers to decide which input or which output you need to drive forward based on the type of instruction that we are dealing with. Then MIPS CPU that we were implementing was a 32-bit machine, or it deals with 32-bit operands. So most of the buses that we see are 32 bits wide. The instruction bus, data bus, they are both 32 bits wide. And the signals inside the CPU are variants of that. You may have, say, separate portions of these 32-bit words travel into different components in the CPU. So the control unit is what regulates the data path. It tells the data path elements what to do based on the opcode and the function field if necessary. So the control unit generates all these possible signals and tells every element whether to write into register, read into register, select some output, some input from a multiplexer. All these things are told by the control unit. So to do that, we had 9 control signals that regulate the data path. And the extra one was the jump signal, which is the 10th output bit of the control unit. We have 9 signals, 10 bits total. Right. So the control signals can be generated by a combinational circuit with the opcode and the function field. Now, all of those things should happen within a single clock cycle. That is the idea of a single cycle implementation. Every instruction is entirely handled within a single clock cycle. Now, to get a better understanding of this, let's look at the data path. What happens in the data path with what happens in a clock. Now, you know what a clock signal is. Clock signal is a square signal, a periodic signal where you have a rising edge and a falling edge coming one after the other, right? So from one rising edge or one positive edge to the next positive edge, we define the clock cycle. And all the operations in a single cycle CPU are supposed to happen within that clock cycle, within one positive clock edge, from one positive clock edge to the next positive clock edge. Within that period, everything is supposed to complete, regardless of what instruction that you're processing. So the first thing that happens on a positive clock edge or rising edge is the program counter is updated with a new address. The value going into the program counter may be PC plus 4, maybe PC plus 4 plus branch offset, or PC plus 4 plus the jump offset, right? So we don't know. Whatever the previous instruction was, the next instruction's address is written to the program counter value at a positive clock edge. So that is the first thing that happens. PC gets updated. That's the first event. The moment the PC gets updated, that updated value goes to the instruction memory, and from that location in the instruction memory, what you can read is an instruction word, the next instruction to be processed, that is wrote into the CPU. This will take some time, but that is what happens. At the start of the positive clock edge, right at that positive clock edge, the program counter gets updated. Soon after that gets updated, the control unit inside the CPU will receive the new instruction, which is brought from the instruction memory. So instead of the old instructions, instruction encoding, now the control unit will have the new instructions encoding just a little bit after the positive clock edge of the clock, right? Okay, so control unit, based on these new instructions of code, the control unit sets the data path signals, so the control signals appropriately, so that the registers are read properly if required, the ALU output is generated if required, or the data memory is read if required, if this is a load instruction, or the branch target address is computed if this was a branch instruction. So all or some of these will happen based on the instruction that we are dealing with, right? So let's go over this again. At the rising edge of the clock, the program counter got updated right at the rising edge, and in a tiny bit of time, the new instruction is propagated into the control unit from the instruction memory. Based on what that new instruction is, some or all of these things may happen, and they will also consume some time. The ALU will consume time, register file will consume time, data memory will consume time, the branch target adder will consume time. So some time will be consumed for this step 2. Finally, several things will happen at the next positive clock edge, next rising clock edge. That is step 3. The register file will be updated or written to for any arithmetic or load word type instruction, arithmetic logic or load word type instruction, where the ALU is generating a result or the data memory is generating a result. If such a result exists, that result is sent to the register file to be written to, and register writing is synchronized to the positive clock edge. So the next positive clock edge will see the value written into the register file for load word or arithmetic logic type instructions. Then if it is a store word instruction, data memory is written to at the next positive clock edge. At the end of that clock cycle, data memory is written, and the program counter is updated to point to the next instruction. So this update to the program counter is the same as this one, the step 1 here, right? At the start of our clock cycle, the positive clock edge, we had the program counter set to updated to the new value, and that is the same thing as at the end of this clock cycle also we'll be updating the program counter. That may be PC plus 4, PC plus 4 plus branch offset, branch target, or PC plus 4 plus the jump target. So whatever the instruction was, the correct value should be written to the program counter, and that writing will happen at the positive clock edge. So every positive clock edge of the clock cycle, the program counter will be updated, and data memory of the register file is also written to. So this process repeats, right? So positive clock edge, PC gets updated to point to a new instruction in the instruction memory. Based on that instruction, within that clock cycle, you will generate the control signals. Register file can be read, ALU can be used to generate a result, data memory can be read to generate a result, or branch target can be computed using the branch target adder. And at the end of the clock cycle, if there are any results to be written to the register file, you will write that. If there are any results to be written to the data memory, you can write that. And the PC will also get written into or updated to point to the next instruction. Right. Now, everything in that step 2 should happen within or between these two positive clock edges in a single cycle implementation. So in the step 2, what did we have? Instruction decoding by the control unit, generation of the control signal, and writing or reading of register files, ALU operations, data memory reading, branch target computation. All those things should happen between the two between the two clock edges. Right. I hope that is clear to you. So let's take a little example, very simple example, and try to understand this concept better, right? So these are the main elements in our data path. We have the instruction memory where the program is, sequence of instruction, and we have the register file to read from register operands if the instruction is requiring register reads, and between them we have a multiplexer to decide where is the right register, which one is the right register given in the instruction. So after the register file we have the ALU, and between those we have the multiplexer and the sign extension unit on the immediate operand if there is an immediate operand, and at the end we have the data memory where if this is a load instruction we read, if this is a store word instruction we write it. And if it is a load word instruction, we need to decide whether to take the load word, the loaded word from the or read word from the memory, or the ALU result to write to the register file. So we have another multiplexer. So these are the major elements in the data path that will consume time. So let's assume the instruction memory reading will take around 2 nanoseconds, right? So we said that the program counter gets updated at a positive clock edge, at a rising clock edge. From that rising clock edge, the instruction memory will take about 2 nanoseconds for the instruction word change and get updated in the control unit. Now, when the read address in the instruction memory changes from the program counter, the corresponding word from the corresponding location will be put onto this bus, this 32-bit bus, and it will take some time for that to happen and the lines or the bus lines in the control units to get updated. Let's assume that is around 2 nanoseconds. And let's assume the time taken by the multiplexer to change its output based on the new input bits that it's receiving is negligible. Let's assume that the multiplexer doesn't take any time. It will take time, it will take a small amount of time, but compared to the instruction memory reading time, let's assume it is negligible, right? The multiplexer's time is negligible. And register file, let's assume is going to take 1 nanosecond. Now, once the input address values changes to read from the register file, not to write, to read from the register file, once the addresses change, it will take about 1 nanosecond for the output lines to have the new result. Once these input address values change, for the output lines to have the new values, new read values from those two register addresses, it will take about 1 nanosecond. That is our assumption on the register file. So register file reading will consume around 1 nanosecond. Instruction memory reading will consume around 2 nanoseconds. Then we'll assume the sign extender and this multiplex also will not consume any time. The time is negligible. And the time for the ALU to generate the result. Once the input operands change here, the time taken by the ALU to generate the output, for the output to appear here in this line, in this 32-bit line, it will take around 2 nanoseconds. That is our assumption on the ALU. ALU will take 2 nanoseconds to produce the result from the moment the inputs change. Then the data memory, let's assume also reading from the data memory will take around 2 nanoseconds. right? So for a load word instruction, when the moment we update the address lines here and the read control signal is asserted, let's assume the moment this address changes, for the data to appear here, it will take 2 nanoseconds. And the time taken by the multiplex, this multiplex also we'll assume negligible, and time taken to write into the register file we can assume that also to be 1 nanoseconds, and the time taken to the data memory we can also assume 2 nanoseconds for the sake of simplicity. But something to note is the writing happens at the next positive clock edge, right? The writing to the registers or the writing to the data memory happens at the end of the cycle, the positive edge at the end of the clock cycle, right? So the time consumed for the writing therefore happens in the next clock cycle, which doesn't really matter if the time taken for the instruction to next instruction to be read and the values along these address lines to be updated is larger than the writing time here, then it doesn't matter. So from the previous instruction, at the end of the clock cycle, we will start writing. It will take about 1 nanosecond to write to the registers. At that same clock edge, it will take about 2 nanoseconds to read the new instruction to come here. So by the time the new instructions register addresses are here, the old values are already updated. So we should be fine. So make a note of that. Right. So now I want you all to look at this and tell me the values for the time taken by these different instructions: load word, store word, add, sub, and o, branch if equal, and jump. So these are mostly the instructions that we were looking at. Add, sub, and o are R-type instructions. So depending on what data path elements are used by these instructions, can you tell me the times taken to complete these instructions? How long does a load word instruction take? Can someone tell me how long does a load word instruction take? The latency for the load word instruction, starting at the time the program counter gets updated from that clock edge, how long do you need for the load word instruction to complete based on these assumed values that we used here for the data path? Load word instruction, the moment the program counter changes, to get the instruction word into this bus line, it will take 2 nanoseconds. Yes? How long in total will it take? So it will take 2 nanoseconds for the instruction to come into the control unit for these bus lines to get updated. And
it will read the register one.
yeah, 1 nanosecond to read base address register value. That is 3 nanoseconds total now, because we neglected the time taken by the multiplexer. And then will the load word instruction use the ALU? Will the load word instruction use the ALU? Yes or no? So for the load word instruction, we have the immediate address offset sign extended going through this multiplexer into the ALU, and the base register value coming from the register file going into that ALU, going to the ALU here. So we assume the sign extender and the multiplexer does not take time, negligible time, right? So the ALU will be used by the load word instruction and it will consume 2 nanoseconds according to our assumption. So 2 here, 3 by the time the registers are read, and 5 nanoseconds will be taken by the time the ALU operation is completed to compute the read address which is sent to the data memory. And the data memory will consume 2 more nanoseconds to produce the result read from the memory from that address. So by the time that result is produced here, it's been 2 plus 1 plus 2 plus 2 nanoseconds, that is 7 nanoseconds total by the time you get the result is produced here. Then we assume the multiplexer will not take time, and then the register file writing will also take 1 nanosecond, but that writing happens at the clock edge, from the clock edge in the next clock cycle, right? So the load word instruction takes how many nanoseconds from the starting positive clock edge to the ending positive clock edge? According to our calculation, can someone tell me? Okay, 7 nanoseconds. Yes, that is correct. So 2, 3, 5, and 7 nanoseconds in order to produce the result at the right data port of the register file. So when the next clock cycle, next positive edge comes, that data will be written to the register file and it will consume 1 nanoseconds at that clock cycle, right? So the time needed between two positive clock edges for the load word instruction is indeed 7 nanoseconds, right? So right, 7 nanoseconds is taken by the load word instruction to complete its operations. Then what about the store word instruction? 2 nanoseconds to read, 1 to read the base address from the register file, 2 to add the base address and the immediate offset in the store word instruction, then writing of the register of the data memory happens at the end of the clock cycle. So yes, we need 5 nanoseconds between two clock cycles for the store word instruction. We need 2 plus 1 plus 2 to produce the right data address and the right data value from the register file at those lines, in those lines. So when the next positive edge, clock edge happens, it will take about 2 nanoseconds to write to the data memory also. So since the next read, since if the next instruction is a read instruction or the load instruction, it will take 1, 2, 3, 5 nanoseconds for the read to start from the data memory. So taking 2 nanoseconds to write the previous value is all right. It doesn't matter. It won't corrupt our values. So for the store word instruction, we have 5 nanoseconds are required to complete the operations. Add instruction, how many nanoseconds? Instruction memory, read the instruction, read the registers, do the ALU operation, produce the result at the start of the at this line for the registers to be written to. How many nanoseconds is that? It's 5. Yeah, 5 nanoseconds. So here we also need 5 nanoseconds to support the add instruction. Sub instruction, again the same thing, right? Read from the instruction memory, figure out it's a R type instruction, then read the register values, perform the ALU operation, and make the result available at the, yes, yeah, that is correct. So all our R type instructions will consume 5 nanoseconds, and O, any R type instruction will use the same data path elements: instruction memory, register file, ALU, and these multiplexers, but we assume the multiplexers will not consume time. So 5 nanoseconds total. What about the branch instruction then? Branch instruction, you read from the instruction memory, then you have to read 2 operands from the register file. The ALU need to subtract those operands and decide the 0 output value, whether the result is 0 or not. Then go and update the adder. Not the adder will happen in parallel to the ALU. Go and update the program counter value, right? If you remember. So how long will that take? 2 for reading instruction memory, 1 for reading register file, 2 for computing the result of the subtraction here. Subtract some register from another register to generate the 0 result value. And that 0 result value go into the AND gate along with a certain control signal to decide whether you need to take the output of another adder which computed the branch target or the regular PC plus 4 value, right? So that addition, that second adder can happen in parallel to what this ALU is doing, right? So they are mutually exclusive operations. While the ALU is doing the subtract operation, the other adder can perform the branch target computation. So we can assume that the branch target computation also consumes 2 nanoseconds, but that 2 nanoseconds happen in parallel to register reading an ALU, because for the branch target, all you need is the this sign extended immediate value plus the PC plus 4 value, which is already available. So that operation can happen in parallel with register reading and ALU operation. So what is the total for the branch if equal instruction then? 2 plus 1 plus 2. Again, 5, right? So 5. Okay. What about the jump instruction? Jump instruction, instruction memory reading, yes, 2 nanoseconds. Will we be reading the register file? Will we be reading the register file for jump instruction? No. Jump instruction is jump to a specific target offset. So 2 nanoseconds to read, then what we have is take the PC plus 4 value, take the 26-bit operand, immediate operand, and concatenate that address. So how long will it take? 2 nanoseconds for sure for reading the instruction memory. From there onwards, it's just about taking the PC plus 4 value, right? That adder PC plus 4 and getting the next this 26-bit immediate offset value and appending it to the top 4 bits of the PC plus 4 value with a shift to left operation. So we can assume that adder PC plus 4 adder will consume 2 nanoseconds, but that 2 nanoseconds can happen in parallel with the instruction memory reading or register file reading. So for let's say sake of safety, we'll assume the PC plus 4 value will take 2 seconds, 2 nanoseconds from the start of the clock cycle, right? So at the start of the clock cycle, at the positive edge, PC gets updated, and from there, the instruction memory will consume 2 nanoseconds to produce the new instruction. At the same clock edge, the adder can start its operation, right? It's a combinational circuit. The adder will take again 2 nanoseconds to produce the PC plus 4 value. So by the time the instruction is read, the PC plus 4 value is available at the end of the adder. So while these two can happen in parallel, the rest of the operation, concatenating and shifting left, well, let's assume they can be negligible. So in total, J will only take 2 nanoseconds to compute or complete, right? So you only need 2 nanoseconds if it's only a jump type instruction. So we can see that these different types of instructions consume different times. So R type, store word, and most of these instructions are need 5 nanoseconds between two positive clock edges. Load word needs 7 nanoseconds between two positive clock edges, and jump only needs 2 nanoseconds between two positive clock edges. So they have different time requirements, but since our implementation is a single cycle implementation, we have to go with the largest value, right? We have to set the clock cycle based on the slowest instruction or the largest time taken by an instruction, which is load word, and set our clock period based on that. So if we set our clock period based on load word instruction to 7 nanoseconds, then all these other instructions have more than enough time to complete within that time period, right? But they will be wasting time. Most of these instructions will be wasting 2 nanoseconds, and if it's a jump instruction, it will be wasting 5 nanoseconds to wait until the next positive clock edge. So any questions with this? Okay, so I'll take only a few more minutes to wrap this topic up so you can start the lab tomorrow. So now if we consider a program after the assembling is done, if there are, say, if the composition of the instructions are like this, if 48% of the program are arithmetic instructions, if 22% of the program are load instructions, 11% of the program are stores, and 19% are branches. If that is the case, then we have set our clock period time based on load, which is the slowest instruction, which takes 7 nanoseconds. Arithmetic and stores take 5, branches also take 5, but some branches like say jumps take 2 nanoseconds. So if we try to compute the time taken by our single cycle implementation, then we have to apply the 7 nanosecond time per instruction for all these types of instructions. But In reality, if we can complete each instruction by the time by only the time it needs, then you can compute a weighted sum, say arithmetic instructions 5 nanoseconds. So 48% of the program will take 5 nanoseconds per instruction. Only 22% of the program will take 7 nanoseconds per instruction, likewise, right? So then you can consume the actual time needed by each instruction to complete separately. So based on that, we have a performance issue at hand for our single cycle implementation. So the longest delay or the critical path determines the clock period. In our case, the load instruction is the critical path. It needs to use the instruction memory, register file, ALU, and the data memory. So it takes the longest delay, 7 nanoseconds. So it is our critical path. The critical path is the data path elements used by the load instruction. Instruction memory, register file, ALU, data memory, and it needs to go to the register file, but that can happen at the next clock edge. Right. So in the single cycle implementation, it's not feasible to change the time period for different instructions because the clock period has to be fixed, and it has to be fixed for the slowest instruction. So it violates our design principle that we had a look at earlier on, making the common case fast. So here you can see the common case is arithmetic instruction. So if you can try to make that fast, that is going to be a good design, an efficient design. But here this single cycle implementation is not an efficient design because we have to stick with the slowest instruction to determine our clock cycles period. So how can we improve performance? We have to go for a multi-cycle implementation. Instead of trying to do everything within one big clock cycle, try to break it down into small clock cycles or small operations for different instructions. For example, say in a multi-cycle CPU setup, different instructions can consume different number of clock cycles based on the actual data path elements that they are really using. So for that, we need to arrange the data path into stages such as instruction fetching, using the instruction memory to read the instruction, and register reading, ALU operation, memory access, register writing. So we can split the data path into several separate stages where each stage should complete within one clock cycle, and that clock cycle can be a lot smaller compared to the clock cycle of the single cycle data path, because in the single cycle data path you need all operations to happen within the same single clock cycle. Here we need only the fetch to happen within a clock cycle, register read to happen within a clock cycle, and so on, right? Each stage to complete within a clock cycle. Then your clock cycle can be smaller, shorter, meaning higher clock frequency. So not all instructions will use all stages. Say an R-type instruction will not do a memory access, so it can ignore that stage. It can go from ALU to register write directly. Some instructions which are not reading register files can ignore that and do the operations necessary only for that instruction. So likewise, you can split this data path into stages and define smaller clock cycle. Now earlier we had one clock cycle for all of these, right? All of these happen within one big clock cycle. Now we have small clock cycles to fit these separate stages. How do you decide the clock period in such a situation? For that, again, you need to go for the slowest stage, not the slowest instruction altogether, but the slowest stage. Usually, the memory access stage is the slowest stage. Say it may take double the time required to write the required to access the register file. Register file, if it is 1 nanosecond, memory access is 2 nanoseconds, something like that. So those are rough numbers, rough examples, but usually memory access is the slower stage, and you can set the clock cycle to fit that stage so that all other faster stages can fit into that clock cycle as well. So then you need to define these stages, what operations go into each stage. You need to define roughly that the time taken for each stage is roughly equal. If you can do that, then you can make the clock cycle as small as possible and get the maximum utilization or maximum efficiency. So that sort of a CPU will be a lot more efficient than what we have in our single cycle implementation. So I will give you some additional reading links to read about some multi-cycle implementations, but we will in the lectures we will look at another way and variant of multi-cycle CPU to improve performance even more than what we can gain here using a technique called pipelining. That is what we are going to discuss in the next topic. So pipelining we will start talking about from the next lecture onwards, that is next week, right? So we will stop here. Do you have any questions? If you don't have any questions, we will stop here.